All right, so here we are. This is lesson 1.8, day 1, solutions to quadratic systems. So if you think back to ninth grade or even 8th grade there, Algebra 1, the systems of linear equations implies two linear equations on the same coordinate plane. So when we graph those, they kind of look like this. There's one line, there's another line, and we talked about the solution, in this case, one solution. Some other options that showed up when we did this, we had two parallel lines, which in that case, we said that there was no solution. And there were a couple of times when we had lines that overlapped one another perfectly, more perfectly than this, and we called that infinitely many solutions. So we're familiar with the idea of systems already when it comes to linear equations. This time now we're going to be talking about solutions of linear and quadratic systems. So as the name implies, we're talking about a line and a parabola on the same coordinate plane. So how might that look? So if I imagine my parabola, there it is, it's opening downwards, and then I'm going to draw a line on the same plane. Well, in this case, we end up with two solutions. That line crosses over that parabola twice, so we would have two solutions. We would identify each one of those xy points. Another possibility here, I'll make this parabola open upwards. Make that just a little bit more parabola-y. There we go. My parabola opens upwards, and maybe my line just kind of touches it once, touches that vertex or another point. In this case, we would have one solution. And when we're talking about parabolas, we've seen sometimes they don't always cross lines that are on the coordinate plane, like those axes. So it's also possible that we could have a parabola existing somewhere, a line existing somewhere else. And in that case, we would have no real solutions. However, that's not going to stop you because last week we were introduced to a new number system. So this is here where we would maybe start to look for complex solutions instead of real solutions. So how would we do this? How would we do this with a real linear quadratic system? Well, there are two ways that we could do this. Oops, excuse me. The first way we could do this is graphically. And that's exactly what it sounds like. We would graph both equations and then look for the intersection. Now, some drawbacks here is that this may not be very precise. If we have a decimal as a coordinate point or a fraction, it may not be precise. We may be having to estimate. The other thing is that this doesn't include our complex solutions. Has an N. We just wouldn't be able to see those complex solutions graphing in the real plane. So there are some limitations to graphing. The other way we could do this is algebraically, just like we solved systems of linear equations. We would use substitution here. So what that would look like is we would set them equal to each other and then solve using any of our solving strategies like factoring or the quadratic formula. So right now, I'd like you to pause the video, go back to your notes and update them. And when we come back, we will look at an example of how we would solve this algebraically and graphically. All right, welcome back. So example 1, we've got a system here. We're going to solve it algebraically and graphically. And I kind of want to start with graphing here just so that I have a visual in mind. Graphing my parabola here, I know that I have the point 0, -3. It's in standard form, so that's helpful. But I also need to find the vertex. So I'm going to use my vertex formula. So that will be -2 divided by 2 times 1, which will simplify to a whopping -1, right? -2 divided by 2 is a -1. So then to find my y value, I'm going to substitute -1 plus 2 times -1 minus 3, and that gives me a y value of -4. So I have a vertex of -1, -4. So I'm going to plot that carefully, -1, -4. And then I have my y-intercept, 0, -3, and its mirror, -2, -3. So now I'm just going to try an x value of 1, just to kind of fill out the picture. Plus 2 times 1 minus 3 is equal to 0. I'm going to save you the work there. I'm not going to show you every calculation. If you don't believe me, you can double check it in your calculator. So we get a couple of extra points here. Now, because I'm solving a system, I may want to look at more than just 5 points of my parabola. So I'm actually going to go one step further just in case. We could always go back and adjust this, add more steps if we need to. But just want to get a full picture here. So when x is 2, my y value is 5, and I get the mirror, -4, 5 as well. So now I'm pretty confident that I've got a pretty detailed picture of that parabola at the very minimum. So glad to see that. And then looking at my linear equation, well, we've got a y-intercept of 0, 3, and a slope of 1. So I'm going to plot that. And my slope of 1 means I'm going up 1, right 1. Whoops, getting a little bit off those points there. I encourage you to use the ruler button while you do this. Don't be like me. All right, so it looks like we intersect at the points more or less -3, 0, and 2, 5. Now, my graph is not super pretty, right? I didn't use the ruler, so it may not be perfect and precise. But here's why we have the algebraic method, is because the algebraic method will help us check our work and make sure that we are precise. So I'm going to zoom in to do that over here so that I have as much space and I'm as clear as possible. So solving this algebraically, I'm going to pick a different setting for this pen, maybe not. Okay. So I'm going to set these equal to each other. So this looks like x plus 3 is equal to x squared plus 2x minus 3. And remember, the way substitution works is if this is equal to y and this is equal to y, then why not replace it? So we've got it set up for substitution, and we know that to solve a quadratic equation, we have to have it set equal to 0. So I'm going to just move some pieces around using my algebraic skills here. And when I simplify, I'm going to get 0 is equal to x squared plus x minus 6. So this looks like something that can be factored, right? If my a times c is going to be -6, and then I can think that 3 times -2 is -6, and 3 plus -2 is equal to 1. I can pretty easily factor this, breaking up that middle term. So when I rewrite this, this will be x squared plus 3x minus 2x minus 6. If you need to review the factoring process, I encourage you to look at our earlier notes on that. So when I split this up, still got 0, it's just hanging out. Looking for that greatest common factor, this would leave me with x times x plus 3 and -2 times x plus 3. So I've got my matching factors and then my outside pieces. So I get 0, is equal to x plus 3 times x minus 2. Now, I'm not really done here, right? All I've done is factor it. Now I actually have to do the solving part of it. So I'm going to set x plus 3 equal to 0, and I'm going to set x minus 2 equal to 0. And when I solve each one of these, I get x equals -3 and x equals 2. So it's looking good so far. This looks like it might match my points, but I won't know until I actually check the y values. So I would be plugging both of those x values in to find the corresponding y value. And I like the linear equation. I think it's easier to work with. Obviously, since this is a system, you could use both equations, but I think the linear equation is going to be just a little bit more friendly. So I'm going to scroll down and I'm going to rewrite that down here for myself. So I would be using y is equal to x plus 3, which in this case is -3 plus 3, which is 0. So I have the coordinate point -3, 0. And then for the other solution, y is equal to 2 plus 3. I'm just substituting x again. So y is equal to 5. And I get the coordinate point 2, 5. So looking at both strategies, looking at both methods, I've got the same pair of solutions. Looks like we've done this well. So at this point, I'd like you to go back to OneNote and update your notes, and then try the next example, example 2, by yourself. And then when you're done, come back and check the rest of the video. All right, so hopefully you tried example 2 on your own. You didn't just wait for me to do it. So first, I'm going to solve this graphically just like the last one. I like having the picture. So I'm going to plot my linear equation first. My y-intercept is 1, and a slope of 2 means I'm going up 2, right 1. If you need to review graphing lines, there's lots of fun videos on the internet about how to do that. So there's my best early morning line there. And then my quadratic, my parabola, I found those x and y values and I made a table on my own. And so those looked like -1, -2, 0, 1, 1, 2, 2, 1, and 3, -2. So I'm just going to plot those points really carefully. Again, I would do that by finding the vertex and then finding the corresponding points that are around that vertex. And so when I plot my parabola, it looks kind of messy in this area. We saw that the point 0, 1 was common to both of them, but I don't know if there's anything else going on in there. So this is where the algebraic method is going to be really helpful to us. So setting this up the same exact way as before, I am going to substitute 2x plus 1 in for y. So I get 2x plus 1 is equal to -x squared plus 2x plus 1. Again, moving some pieces around. Minus 2x minus 1. So I'm going to get 0 is equal to -x squared. Ooh, plus 0x plus 0. So you may have gotten here and thought, ugh, what is going on? If we simplify this, though, we get 0 is equal to -x squared. And when I think about this, something times itself made negative is equal to 0. There's only one possible option there. X is 0. So if I use that linear equation again and substitute to find my y value, y is equal to 2 times 0 plus 1. So y is just equal to a whopping 1. So I do, in fact, get the same single solution here. This is like one of those examples where we only have one solution. So 0, 1 is the only solution. So if you didn't quite get this one right or you got stuck somewhere, I encourage you to look back at your work. Was your parabola plotted correctly in the first place? Or did you have any issues with the algebraic method there? I'm going to do one more example here with you, just so that you have something to look at. This one's going to be a little bit more tricky because this parabola is not super friendly. And it starts right away with the vertex, but that's not going to stop us. So our vertex here, if I use negative b divided by 2 times a, that's going to be the opposite of negative 5 divided by 2 times 2. So I get a negative, or I'm sorry, negative times a negative makes a positive. I get a positive 5/4. Now, anytime we're working with that, 1.25, our graph suddenly becomes a whole lot less precise because we've got decimals involved and potentially decimal solutions. So I'm going to substitute here to find the y value of my vertex. And when I run that all through my calculator, I get negative 1.125. So that is going to be maybe this point right down here if I'm super careful. But again, I'm not perfect. Humans aren't perfect, so we might have some imprecision in our graphs here. So finding some other x values around that are going to certainly give us a better picture, but already I think we can see that we're going to have some issues with the precision of our graph. So 1, -1. Now I can't just say that it's 2, -1 also because my vertex isn't right smack dab in the middle. So I'm going to run this again with an x value of 2. Just to be sure, and I actually get 0 there. So it's not perfectly symmetric, or symmetric in the way that we would normally look at it because our vertex is kind of off-centered there. We have the y-intercept of 0, 2. So if we're really careful, we can start to see kind of the points around it. I encourage you, if you're not sure, to plot in some other x values, maybe not all just whole numbers. So our parabola looks like this. And then having a line x minus 2, I have my y-intercept of -2, going up 1, right 1. And I'm going to graph that carefully. So it looks to me like my solutions might be 1, -1, and 2, 0. But this is where I'm really glad to have algebra in my toolkit because I can check to be sure. So just like every other time before this, we're going to start by substituting x minus 2 in for y. So we get x minus 2, I'm just going to cut that off there, I'll get confused. 2x squared minus 5x plus 2. So little bit of algebra, adding 2, all together. We're going to get 0 is equal to 2x squared minus 6x plus 4. Now again, we could use any method we wanted to. We could use factoring, we could use the quadratic formula. I'm awfully fond of factoring here because I see a greatest common factor of 2 that I'm going to factor out. And then using my factoring strategies, I would get this to factor to 2 times x minus 2 times x minus 1. And if you need to go back and work out that factorization for yourself, I encourage you to do that. So to continue solving here, I'm going to set both little pieces equal to 0. So I get x equals 2. And then x minus 1 is equal to 0. I get x equals 1. So once again, we're looking good. Those start to match our points. We just have to verify with the y value. So my equation was x minus 2. So I'm going to replace x. 2 minus 2 gives me 0. So I have the point 2, 0. And over here, y equals x minus 2. I'm going to get 1 minus 2 or -1. So I have the coordinate point 1, -1. And it looks like those solutions match, which is exactly what we're looking for. So That was a pretty fast process. Your assignment's only a couple of questions just to start to get our feet wet. And tomorrow we will, of course, answer any questions that you have. So after you finish up your notes in OneNote, I want you to go over to that practice assignment and begin to work on it. Of course, you can work with other people in your class. They're going to be good resources for you. So I will see you when I get back tomorrow. Bye.